Hello students, welcome to Online classes. In this class we will discuss lenses, refraction through lenses, and we will see lens maker's formula. Let us start discussion on the concept of lenses. Today's concept is lenses. This is extend part of refraction through spherical surface. Generally, lenses are nothing but optical medium bounded by two spherical refracting surface, of which at least one is a spherical. How it is? The homogeneous optical medium bounded by two spherical refracting surface, out of which one must be spherical. That we are calling lenses. Shall I define lens? The optical medium bounded by two surfaces of which one must be spherical. One must be spherical. That we are calling lens. If both are spherical, then doesn't matter. Out of two surface, one must be spherical. That we are calling lens. So many types of lens are available: biconvex lens, biconcave lens, plano-convex lens, plano-concave lens. So many types are available. Let us see different types of lens I will draw. See here. This is one type of lens. This lens is nothing but biconvex lens. This is biconvex lens. Here both the surfaces are spherical. This we are calling biconvex lens. See here. Then one more type of lens available. This is one more type of lens. This we are calling biconcave lens. Here both surfaces are spherical again. Let us take one more type of lens. Shall I take this lens? This lens I can call plano-convex lens. In this case, what happened? One surface is spherical and the surface is plane, right? Then one more type of lens I will take. Look at me. This is one more type of lens I can take. This is plano-concave lens. Plano-convex lens. How can call this? I can call biconvex lens. This I can call biconcave. This is plano-convex lens. And this is plano-concave lens. Different type of lens are available, but our main intention is to study biconvex lens and concave lens. Both lenses we'll see, and how the refraction of light takes place, that we'll see now. See here. This lens I can call biconvex lens. This lens I can call biconcave lens. This biconvex lens simply you can call converging lens, because it converges the ray of light after refraction. And the biconcave lens we are calling divergent lens, because it diverges the ray of light after refraction. Listen here. How refraction of light takes place in case of lens, and how ray of light is converges, and what is optical center, how to define focal length and principal focus, that we'll see now. Look at me. Initially we will define one term that we are calling optical center. See here, this is one convex lens. This convex lens I can take this point is nothing but O point, this point or this point I can call O point, through which the ray of light is never deviated. See here, how it is? Optical center means wherever the ray of light incident, this ray of light never deviated. Instead, the ray of light can pass us through same line. So this point I can call optical center. Or see here, Again I can take here one more points here within the lens. The point within the lens through which the ray of light never deviated, that point I can call optical center. So here this also optical center. So whenever ray of light incident, how the ray of light can go? Ray of light can go like this, in this direction. I mean the point within the lens, either for concave lens or convex lens, the ray of light never deviated, that point we are calling optical center. This point I can call optical center. Right thing. Then in case of biconvex lens or simply convex lens, how the ray of light incident after refraction, how to take the radius of curvature and how to take the principal focus, that we'll see. Look at me. So simply I can go for convex lens. In convex lens, how the ray of light can incident and how get refracted. After refraction, how the ray of light can meets, that point we will see. Look at me. Simply I can take this is one convex lens, or we can call biconvex lens. Convex lens I can call. Initially we define convex lens. The lens which is thicker at center and thinner at edges, that we are calling convex lens. How this is? The lens which is thicker at middle, thinner at edges, that lens we are calling convex lens. Then the point within the lens, this point I can call optical center. This point I can call optical center. Now an imaginary line which is passes through optical center, that we are calling principal axis. How it is? See here, this is nothing but the line passes through optical center, this we are calling principal axis. This we can call principal axis. Later on this. Now what is the assumption? If the ray of light passes through principal axis, the ray of light is never deviated. Remember this point. Now let us take the number of rays of light which is incident on given convex lens. How it is? This is one ray of light incident at this point. After incident, the ray of light can refracted like this. In this way ray of light is refracted. One more ray of light that is passes through principal axis, so that this ray of light never deviated. How it is? Let us take the ray of light which is passes through optical center and principal axis. This ray of light is never deviated. After refraction, it can meet at this point. Now, one more ray of light will take. See here, this is nothing but one more ray of light incident at this point. After refraction, how it comes? It comes like this. What we know? After refraction, all the rays of light meeting at this point I can call principal focus. What you can call principal focus. Then the distance between optical center and principal focus, what are calling this? This we are calling focal length. This I can call focal length. Right. Then along the direction of incident ray, according to sign convention, along the direction of incident ray, all distance are taken to be positive. So that how to take this OF? OF is nothing but what value? Focal length. This focal length can be represented by F value, and for convex lens, focal length can be taken to be positive. Because according to sign convention, along the direction of incident ray, all distance are taken to be positive. So that for a given convex lens, the focal length always taken to be positive. Now let us take one more type of lens. We are taking biconcave lens or simply concave lens. How the structure looks like for concave lens? This I can call concave lens. This I can call concave lens. How to define concave lens? The lens which is thinner at middle and thicker at edges. The lens which is thinner at middle, thicker at edges, that lens we are calling concave lens. Again, the point within the lens such that the ray of light never deviated, that point we are calling optical center. This I can call optical center, or can represent by C also, doesn't matter. Now again, imaginary line which is joining through optical center, that we are calling principal axis. Right around this. What we know? Whenever ray of light incident on concave lens, how refraction takes place, that we'll see now. See here. Whenever the ray of light incident at this point, after refraction, how the ray of light can go? Ray of light can go like this. Or you can take like this also. After refraction, how the ray of light can go? Ray of light can go like this. Again, if the ray of light passes through principal axis, this ray of light never deviated according to assumption. Again, one more ray of light. See here. This is one more ray of light incident at this point. After refraction, how it can go? It can go like this. In this direction it moves. After refraction, here rays of lights are deviated, diverges. So if I produce the divergence ray of light in backward direction, where they meets? See here. This is one refracted ray. If refracted ray produced in backward, it can meet on principal axis like this. Right? Similarly, if I produce this refracted ray in backward direction, where the meet on principal axis, it can meet on principal axis. This point I can call principal focus. This I can call principal focus. What is principal focus? After refraction, if the rays of light meets on principal axis, that point we are calling principal focus. Now, the distance between optical center and principal focus, what we are calling this? This is focal length. How to take? This OF I can taken as focal length, but how to take here focal length? All distance are measured from optical center, first point. Distance between optical center and principal focus we are calling focal length, and this focal length is opposite to direction of incident ray. Opposite to direction of incident ray, all distance are taken to be negative. So that for concave lens, principal focus is always taken to be negative value. And for convex lens, the focal length is always taken to be positive value. But whenever convex lens is there or concave lens is there, we know focal length. This we are calling focal length. How this focal length depend? This focal length depends actually on the radius of curvature of two refracting surface. See here. Here we are calling this is one refracting surface and this is second refracting surface. Spherical refracting surface. Here also two spherical refracting surfaces are available. Right? This focal length mainly depends on radius of curvature of two spherical surface. This is one spherical surface, this is second spherical surface. Right thing? Right. This also one spherical surface, this also one spherical surface. So this focal length, it mainly depends on radius of curvature of two refracting surface, depends on wavelength of light used and depends on refractive index. So there is relation connecting among focal length, radius of curvature and refractive index of the medium. Before that, we should know one formula that we are calling lens formula. How lens formula can be taken, that we will see now here. Directly, this lens formula is not for our syllabus, simply I will mention the equation. Look at here. Now, simply I can take, this is one convex lens. This is one convex lens I can take. Thin convex lens I can take. So this we are calling optical center and principal axis. Right? Look at here. Whenever the ray of light incident on principal axis, this ray of light incident on the lens, after incident the ray of light can refract it and meets on principal axis. Right around this. The ray of light meeting on principal axis, this point I can call image. Here two terms we are defining. One what we are calling object distance between optical center and object is called as object distance. Distance between optical center and image, what you are calling image distance. Right. The relation connecting among focal length, object distance and image distance, that we are calling lens formula. How the lens formula is that? Simply lens formula can be taken 1 divided by f is equal to 1 divided by v minus 1 divided by u. This formula we are calling lens formula. What we are calling this? Lens formula. This lens formula not for our derivation, just remember this formula. Then we know we need relation between focal length, radius of curvature and refractive index. So that formula we are calling lens maker's formula. To understand lens maker's formula, we should know two terms: refraction through convex spherical refracting surface and refraction through concave spherical refracting surface. This relation already we have seen in the previous class, that is in lecture number 8 already we have seen. Now let us see what is mean by lens maker's formula, how lens maker's formula can be obtained. Look at me. Now next concept is lens maker's formula. See here. Next concept is lens maker's formula. Look at me. Today's class is concerned to lens maker's formula. It is very important. Very important this lens maker's formula for further study of refraction through lenses. Look at me. Initially we will derive lens maker's formula, then what is significance of this lens maker's formula, that we will see now in detail. Right. Look at me. This lens maker's formula, it can valid both for convex lens and concave lens. For our syllabus, we should know about the convex lens, how refraction takes place in the convex lens, that we will see. Look at me. Now initially, to understand this lens maker's formula, we will take a biconvex lens, or simply we are calling convex lens, or thin convex lens. Thin convex lens. This is one convex lens. Right. Now here two surfaces are there. One we are calling what? Let us take, we are calling this is the optical center. Say this optical center shall I represent by C value? You can represent O also, no matter. Now the imaginary line which is passes through the imaginary line which is passes through optical center, that we are calling principal axis. Right. Now consider the ray of light, consider the object situated on principal axis. What is the assumption here? The object is situated on the principal axis. Look at me. See here, consider this is one object situated on this principal axis at O. We know that two surfaces are there. One surface is ABC, for my convenience shall I take? So this I can take C, I can take this D, ABD, and this is what value AED, like this. Two surfaces are there. So simply shall I take this? Or to remove the confusion, I can take it is ABC. So this is optical center O, and somewhere object is available. Say the object available at P point, and this surface looks like what value? ADC. Two spherical surfaces are there. One we are calling ABC, second one we are calling ADC. The ABC surface is a convex spherical surface. ADC surface is a concave spherical surface. Right, concave spherical refracting surface. Now, whenever the ray of light incident on the surface ABC, let us take which ray of light? I can take nothing but PN is the ray of light incident on the surface ABC. After incident, the ray of light can refracted. Look at me. How the ray of light can refracted? A ray of light can refracted like this. Again, after refraction, how the ray of light can meet? Ray of light can meet on principal axis like this. How it is? The ray of light can meet on principal axis at point I. Then what to assume? The distance between optical center and object is called as object distance. The distance between optical center and image is called as image distance. But students, the formation of the image can consider in two ways. Formation of the image can consider in two ways. One way is in absence of surface ADC, and in presence of surface ADC. We know that if the surface ADC is present, where the image can appear at I point. But whenever the surface ADC is absent, where the image can appear, whenever surface ADC is absent, then this refracted ray, where they can meet, it can meet at some other point. At what point? It can meet on the point what value? I dash. I mean, in absence of surface ADC, the refracted ray can meet on principal axis at I dash point, so that image can appear at I dash. So We can call distance between optical center and object, we are calling object distance. This is represented by u, and in presence of surface image appeared at v. But in absence of surface ADC, where the image can appear at this point, that is v dash point. Are you following? Right thing? Then now formation of the image consider in two ways. One way is what? In absence of surface ADC, in presence of surface ADC. Now we'll see. In absence of surface ADC, we will see image. How separate diagram looks like. Look at me. See here, shall I take here? Formation of the image in absence of surface ADC. Image in absence. Image in absence of ADC. Are you following? How it is? Look at me. In absence means this ADC is absent. How to take? I can take this, nothing but spherical refracting surface. This is principal focus. Sorry, this is principal axis. Right thing. This we are calling what? Center of curvature C point. Right, which surface this is? This is one surface. Let us take this surface. I can take A, B, C. Right around this. Where the object available? Object available at this point. Say object is available at P point. Whenever the ray of light incident at this point, at what point? N point. The normal drawn at point of incident from optical center of curvature. After refraction, where the ray of light can meet? After refraction, the ray of light can meet at this point. At what point? Ray of light can meet at I dash point. Where it is? It is in absence of surface ADC. Right? Done. So this has the spherical refracting surface refractive index N2, and what about this refractive index N1? Right or wrong? See here. Distance between optical center and object, what are calling this object distance? It is represented by what value? U. Distance between optical center and image, what are calling this image distance? V. Right on this. But we know one condition. Condition is what? Refraction through convex spherical refracting surface. We know relation. Already we obtained in the last class. What it is? In the last class we obtained minus N1 divided by U plus N2 divided by V is equal to N2 minus N1 divided by what value? R value. Right on this. Then here where the object is available? Object available at U. So that in this case how to take? In this case I can take U is equal to U only, but where the image can appear? Image can appear at V dash. So that simply I will take V is equal to what value? V dash. And this is one spherical refracting surface. It has radius of curvature. So shall I take for this radius of curvature? I can take R can be replaced by R1. Got my point? Now, by taking this convention, what about our equation? How it is? Simply I will take what it is minus N1 divided by U plus how much? N2 divided by V dash is equal to N2 minus N1 divided by R1. Let us call this is equation number 1. Equation number 1, where it is the formation of the image in absence of surface ADC. But if the surface ADC also present, where the image can appear at I point. Shall I draw a separate diagram for it? How to take? Again, this is one spherical refracting surface, I mean concave spherical refracting surface. Which one it is looks like? This looks like what value? ADC. This I can call principal axis. Are you following me? How the refraction takes place? Refraction can take place like this. Shall I take here? Look at me. How the refraction can take place? Like this refraction can take place. Where the image can appear? Image can appear at I point. And where extended actually? This is extended. Right out of this. Now actually this is nothing but normal drawn at the point of incident from optical center C. Now in this case what happened? Actually this point what I can call? This point I can call I dash. In this case what happened? I can take this is act as object this is act as object and this is act as image. So this becomes image like this. It is V dash. I mean here image can be taken as object distance, because if it looks like this, this becomes object, this becomes image, this becomes object. So for concave spherical refracting surface we know relation. Simply reverse of this. How to write? Look at me. I can take minus n1 divided by u plus what value? n2 divided by v minus n2 divided by u plus n1 divided by v is equal to what value? n1 minus n2 divided by what value? R value. But if you stand here, so this is act as object and this is act as image. Where the object was available actually? Object was available at this point. This point object was available. Right around this. Now, how it is? Look at me. In this case, I will take this is act as V dash. V dash is equal to what value? U. And what about this? This is act as image V. Are you following this? In this case, just reverse of this. Reverse of this means here U can be replaced by V dash. U can be replaced by V dash and V is equal to V only, and this radius of curvature has value R is equal to R2. Right out of this. Then what about above equation now? Above equation becomes now what value? N2 divided by V dash plus N1 divided by V is equal to what value? N1 minus N2 whole divided by R2. Let us call this is equation number 2 now. Right there. Equation 1 must be like this. In absence of surface ADC, in presence of surface ADC, equation must be like this. Now, to obtain lens maker's formula, what to do? Simply add equation 1 and equation 2. If you add equation 1 and 2, clearly you can get what is lens maker's formula. Look at it here. LHS of equation 1, what will take? Minus N1 divided by U plus N2 divided by V dash plus RHS of this one, plus into minus, this becomes minus directly because it is plus here minus. So minus N2 divided by V dash plus N1 divided by V. Right or wrong? Shall I write here directly? So to add equation 1 and 2, look at me here. Simply I am going to add equation 1 and 2. Equation 1 is like this. What about this? Minus N1 divided by U plus what value? N2 divided by V dash minus of LHS of this. N2 divided by V dash plus N1 divided by V is equal to RHS of this. N2 minus N1 divided by R1. N2 minus N1 divided by R1 plus N1 minus N2 divided by what value? R2. Right around this. Here what values get cancelled? N2 by V dash, N2 by V dash get cancelled. What is remaining here? Look at me. So minus N1 divided by U plus N1 divided by V is equal to how much? N2 minus N1 divided by R1 plus of N1 minus N2 divided by R2. Right around this. Simply I can make it reverse way. Here N1 minus N2 divided by R2 is available. Shall I make it reverse? Reverse mean I can write N2 minus N1 divided by minus R2. This step I can write. How to write? This step N2 minus N1 divided by minus R2 I can write. Shall I directly here this step? This step I can write directly. Look at here. How to write? This step simply I can write N2 minus N1 divided by minus R2. I write this step like this. Then here what is common? N1 is common. Here N1 common. N1 common mean, look at me here. How to write? N1 divided by minus 1 divided by U plus 1 divided by V. Right. Here what is common? N2 minus N1 is common. N2 minus N1. Look at me. See here. How to write? Shall I remove this? N1 is common. Into bracket minus 1 divided by U plus 1 divided by V is equal to N2 minus N1 is common. What is remaining? 1 divided by R1 minus 1 divided by R2. Write on this. Or else I can write like this. How to write? This step I can write 1 divided by V minus 1 divided by U. N1 bring this side is equal to N2 minus N1 divided by N1 into bracket 1 divided by R1 minus 1 divided by R2. Or else we know lens formula. What is lens formula for this? Already we obtained 1 divided by F is equal to 1 divided by V minus 1 divided by U. This is lens formula. 1 divided by V minus 1 divided by U is equal to 1 divided by F is equal to, how to write? So N2 divided by N1 minus 1 I can write this value into bracket. How much? Into bracket 1 divided by R1 minus 1 divided by R2. Or else, if the case this value has refractive index N2 and this value has refractive index N1, it is N1 and this is N2. Right or on this? If the case N2 is equal to N and N1 is equal to 1. N2 is equal to N and N2 is equal to 1. Then what formula we got? 1 divided by F is equal to what value? N minus 1. N minus 1. N minus 1 into 1 divided by R1 minus 1 divided by R2. This formula we are calling lens maker's formula. I mean the relation connecting focal length, refractive index and radius of curvature, this formula we are calling lens maker's formula. This lens maker's formula used for lens manufacturer to remove the human defect type. I mean to required focal length, lens manufacturer use this formula. So this name we are taking as lens maker's formula. And required focal length can be used to magnifying the image of the object or used in telescopes or used in microscopes. For that purpose we are calling lens maker's formula can be used to get required focal length. I mean human has so many defects that we are calling astigmatism, that we are calling so many types of defects are available. One we are calling astigmatism, second one we are calling presbyopia, and so many types of defects are available. To remove the human defect side, generally lens maker's formula can be used for a given focal length. See here, this lens maker's formula not only uses for convex lens, it also uses for concave lens. But for your syllabus, only we have the convex lens formula, and the concave lens formula can be, you can take also as you wish. So up to here, the convex lens and required focal length of the given lens can be obtained by using convex lens, that we are calling lens maker's formula. The further study of lenses and related phenomena that we will see in the next session. Thank you.